Okay, welcome back, Physics 30. This is the third video in MP1.2. So yes, we saw this factor here that is applied to our time on the ship, which has profound consequences here that occur when we're traveling at really high speeds, significantly high speeds, above, let's say, 10 to the 6, in which, again, the gamma doesn't change that much. If I'm going that fraction, it's only 1.000006, but it's still substantial. The concept of time dilation may be hard to accept. It contradicts our experience. We can see that from an earlier equation that the time dilation effect indeed is negligible unless v is reasonably close to the speed of light. If v is less than c, we get this factor being smaller than 1, and basically what happens, of course, is that the two times are equal. But even at any speed, you will see that it does have an effect, a really small one. Speeds we experience in everyday life are much smaller than c, so it's little wonder why we don't really notice this time dilation. But experiments that have tested the time dilation effect have confirmed Einstein's prediction. For example, in 1971, extremely precise atomic clocks were flown around the Earth in jet planes. The speed of planes is only 1,000 kilometers per hour, which is really slow compared to the speed of light. So the clocks had to be very accurate, going quite a few decimal places in the time department in order to detect time dilation. So if I had two identical clocks, one on Earth, one sent out in planes, and then we come back and we would see that, oh my gosh, there was a difference. There was a difference, that the clocks no longer are running at the same pace. Time dilation had been confirmed decades earlier, however, by observations on elementary particles, which have a very small mass and therefore can travel at close to the speeds of light. We're talking about really small particles. Many of these elementary particles are not stable and decay after a certain time. One example is the muon, which has a mean lifetime of 2.2 microseconds when at rest. Careful experiments show that when a muon is traveling at high speeds, though, its lifetime is measured to be longer than it was at rest, as predicted. So we're going to run through that calculation and see exactly how does that come to be. How does that work? So if we take a look at this, if we could accelerate the muon at 0.6 c, which basically means 60% of speed of light. Okay, so 60% of the speed of light. That's very quick. 1.8 times 10 to the 8, as we'll see. Now, a muon's lifetime at rest, according to a muon, it lives this long, a really short time, here and gone. So if we take, we're going to look at this in two different ways. We're going to use exact speed values, and then we're going to use c values, as you'll see. So delta t is equal to delta t naught over the square root of 1 minus v squared over c squared. Okay? So we have that. So the time that we measure in the lab, we're looking for that, and we're comparing it to what the muon experiences. The muon would experience this time, 2.2 times 10 to the minus 6. And that muon is traveling at this speed, according to us in the lab, watching all of this. And the speed of light, of course, is 3 times 10 to the 8. So when you're doing this on your calculator, make sure you use brackets here, because you're going to be squaring all of that. Now what we get here is, when we do that, of course we're going to get a value here that's less than 1. We're going to subtract it from 1, so we will have a number on the bottom of this equation. That number works out to be this. So you can work this out on your, in fact, I recommend you work this out on your calculator just to make sure you get that answer. Look at that. The muon experiences 2.2 times 10 to the minus 6, but in the lab we see that the muon has lived for 2.75 times 10 to the 6. Muon has lived longer, according to the scientists measuring. Now, it doesn't seem like much when we're talking about these time periods, but it's drastic if you're talking about extended time periods. Let's look at another way of looking at this, kind of an easier way, easier on the calculator, so to speak. So what we can do, again, write this as 2.2 times 10 to the minus 6. But this time, let's talk about the speed of light in terms of c. So the speed of light is c squared. And whenever you see the letter c, that automatically means 3 times 10 to the 8. And this is 0.6 of c, 0.6 c. And of course, we're squaring that, right? We are squaring that. So c squared and 0.6 c all squared. So we can do it this way, and it makes it a little bit easier. So on the bottom, we'll get 0.36 c squared over c squared. And notice what happens here. C squareds and c squareds cancel. So it's going to be 2.2 times 10 to the minus 6 all over. Now 1 minus 0.36 is 0.64. So that's a little bit easier to do in your calculator. And guess what? We get the same answer. 2.75 times 10 to the minus 6 seconds. So in the lab, we see that the muon is living longer than the muon experiences itself. So the equation is true only when T naught represents the time interval between the two events in a reference frame where an observer is at rest and sees the two events occurring at the same point in space. So it refers to the person that they think they're at rest. Okay, so they're actually in the moving vehicle. They think they're at rest. This is what they register. The time interval T naught is sometimes called the proper time. So the person that's in the spaceship moving away from someone else, according to them, they're standing still. So that's the proper time. And then the delta T represents the time interval between the two events as measured in a reference frame in which that object is moving with the speed v respect to the first. So in the previous example, delta T was equal, so the muon experiences this time because according to it, it's at rest. Whereas the persons that are doing the measurements, the proper time, and you can always think of it as this too, the delta T is always the shortest time. So it's the one that the person, they feel they're at rest, that's what they experience. Whereas delta T is going to be bigger because they're considered the outside observer watching everything happen. Okay, so let's look at a real example now, one that we can understand. A car traveling at 100 kilometers per hour covers a certain distance in 10 seconds according to the driver's watch. What does an observer on Earth see? So we have this, then we have the car over here, this person speeding away, zoom, zoom, going that way, and they're saying, oh, it's taking me 10 seconds to travel this far. And this person is thinking, okay, how long is it to me? So we're going to do it with a regular speed, then we'll look at it in terms of a really fast speed. So so delta T equals delta T naught all over 1 minus v squared over c squared. So over here we have, so this person experiences 10 seconds. Now, 100 kilometers per hour. Of course, we know how to quickly change it into meters per second divided by 3.6, right? And when we do that, we get 27.8 meters per second. So this is so the speed of the car is 27.8 meters per second. So we're going to have to square that. And 3 times 10 to the 8 all squared. And when we do that, of course, this is a really tiny number compared to this. For all intent and purpose, this is going to be very close to 0, but it still is a number. And we look at our calculators. Now, our calculators don't go very many decimals. We would perceive it to be 10 seconds. But if our calculator could go further, we would see that there is a slight difference. It would be slightly longer than 10 seconds. But unfortunately, our calculators don't go that far. So if we had really precise measuring instruments, we would see that, oh my gosh, even with a car moving at 100 kilometers per hour, there is a slight difference. And it's really interesting when you think about this and all the events that happen on Earth all the time of things moving. All these little time differences. Now, if we repeat this with 0.9 c, so 90% of the speed of the light, So that car is likely almost as fast as a Kia Rondo. Do the same thing. So we would have, so according to the person in the car, they're taking 10 seconds to go a certain distance. The person measuring it, though, if that person is moving away from them at 0.9 c, and of course we have to square that whole c part. Oh, and this stays as c squared. I'm going to leave them as that. Okay, so that's going to give us 10 all over 1 minus 0.81 c squared over c squared. All right, so it'll give us 10 divided by 1 minus, what did we get there, 0.19 c squared. Oops, I guess the c squared's canceled up here. We get that, and then we would get this. Look at that. So the person in the car experiences 10 seconds. To an outside observer, they would say, oh, no, you don't. You don't experience 10 seconds. You experience 23 seconds. So isn't that interesting? The person at rest experiences more time than the person in the moving vehicle. And the cruncher is that they are both correct. All right, we'll stop it there, and we'll come back and do the next section.